Let's talk about the atomic structure and the principle behind this topic. Now, before the Bohr theory, there were obviously a lot of other different theories, but we are going to talk only about the first one before that, which is the Rutherford's theory of how an atom should look like. So according to Rutherford's theory, the atom should look like this. So you have a nucleus. You have a nucleus in the middle, and the nucleus consists of positively charged protons and neutrons, as we discussed in the previous segments. So these two, they make up the nucleus. Okay, protons orbiting around basically like planets. Like planets orbits around the sun. So it's almost like that. You have electrons, or in this case, one electron orbits around the positively charged, and also there are some neutrons as well in the nucleus. Now, this theory was accepted for quite some times, like this, and then you have another electrons, for instance, right here, that also orbits around the nucleus. Now, the problem with this theory is that when you have a positive charged core, so this one is positively charged and this one is negatively charged, and we know that positive charge and negative charge, they attract each other, correct? Meaning that at some point the oppositely charged particles, they would be able to interact, and the electrons will at some point collapse into the nucleus. If this collapse, then of course the atoms will no longer exist anymore. Now, Bohr here, he addressed this theory, this lack of explanation regarding the collapse of electron into the nucleus. So in his contribution, he suggests that, so this is the most important part of his contribution, he suggests that the electrons occupy stable orbits with quantized energy. Now, in this theory, we can first erase this. Based on the Bohr's theory, now we can make a different model to the proposed how the atom should look like. Now, in this theory, let me try to draw a shape here. Okay, 1 and then 2. For instance, 2. So you also still have this orbits, okay? You have electron here, you have electron there. However, now they have certain quantized energy for each of the level of the orbits. Okay? Now, Bohr also theorized that the electrons occupy just one of the orbits in a stable manner, which they cannot deviate without absorbing or emitting energy in form of light. So now we will transition into the next topic that we are going to talk about. We will revisit this later, but now we have to talk about light, because in this case, we will also talk about how electrons like this, they can move up, they can move up or they can move down the energy, the different quantized energy levels due to absorbing or emitting light. Therefore, first we are going to talk about light. Light is a wave and also a particle. As a wave, we have central characteristics that can be defined by 4 variables, which are: we can identify the so-called wavelength, lambda as the symbol, frequency, velocity, and amplitude. Now, if we take a look at how a wave propagates, like this. Okay, let me try to draw the wave first. Say it looks something like this. Okay, now this is what we call as the wavelength. That is what we call as lambda, or the wavelength. It's defined as any wave, for any wave, as the distance between the corresponding points on adjacent waves. So from here, if we take half of this, it's to this half. So this is the wavelength, and this one is what we call as the amplitude. Amplitude. I will draw it one more time with different colors so it's fully clear to you. This is the amplitude. Amplitude is sort of the size or height of the wave. Okay. On the other hand, the frequency over here is defined as the complete cycles, the number of complete cycles. Number of complete cycles of wave, of course, that passing a given point per second. So this is normally defined over a time frame which is likely to be second. That's why the unit for frequency, or the symbol is this one, nu, is measured in the unit of 1/second, or this can also be called as the hertz. Hertz, Hertz. Now, frequency and wavelength, they are not independent of one another. So there is a correlation between frequency and wavelength. Now, to understand this, we also have another parameter that is called the velocity, which is the speed of light. And in this case, normally the speed of light in vacuum, so the speed of light, but this is defined in vacuum, that we symbolize as c, and c is around 3 multiplied by 10 power to the 8th meter over second. Now this speed of light is a constant. Okay, and therefore, based on the speed of light, there is a derivation that result in this formula where c is lambda times nu. Okay, so if you multiply the wavelength of a wave, so this, with the frequency over second, or also we call it hertz, then you will get the speed of light, which is 3 times 10 power to the 8th meter over second. Yeah. So this is one formula that is very handy that you can use in this topic. Now we're looking at the so-called electromagnetic spectrum. Which also contains the visible light. So as you can see in here, visible light is actually just a small portion of the entire spectrum of electromagnetic spectrum that this one is the part where our eyes can detect. Yeah, there are other regions like gamma rays, X-rays, for instance, for medical applications. Yeah, also there's microwave, radio waves, and also long radio waves. Now for visible spectrum, you can see down here you have different colors from red to purple or purplish. Now you can see here this is the wavelength from 400 nanometer. Normally the dimension is in nanometer, so from 400 to up to around 7 or 800, and 800 is the color of red. Now the most important thing from this picture is that this picture I took from the book, the textbook that we are using in this lecture. The most important thing is that from radio waves up to the gamma rays, the energy increases. Yeah, so from red to purple, the energy increases. So this area has the highest energy in the visible spectrum. However, the wavelength is actually the exact opposite of energy. While the energy increase from here, from this point up to that point, the wavelength is actually decreasing. So as you can see, the wavelength here is 400 and here is 700. So from here, we know that wavelength, which is lambda in symbols, is actually correlate reciprocally with the energy. Yeah, the higher the energy is, the lower the wavelength is, and of course vice versa. Now we will discuss light as a particle. Yeah, this idea came from an experiment by Albert Einstein, and this one is the one that actually won him his Nobel Prize. He did find this phenomenon that is called the photoelectric effect. Yeah, in this experiment, what he did was there was a piece of metal. Yeah, so this is a metal, and when light is shone through it, actually he observed that there is an electron being ejected. Yeah, so you can imagine there is something that we long knew as wave. It hits a particle, and a particle, electron in this case, was ejected. And you can imagine that this can only happen based on Einstein's conclusion, because light also has the properties of particle, because only particle can hit another particle and eject this particle out of its place. Therefore, from here, the theory of wave-particle duality was born. Yeah, duality. Okay. Now Einstein also introduced the concept of photons. Okay, so photons was described as a collection of packets of energy. So collection that also has the identity of a particle. Yeah, due to this experiment that won Einstein his Nobel Prize. And from here, the energy of a photon, it has energy. The energy is equal to h, which is a constant, times the frequency as a wave. Yeah. So h is what we call the Planck constant, named after Max Planck, German scientist, which is equal to 6.63 times 10 power to the minus 34th joule second. Okay, and we know from our discussion before that frequency v is equal to c, which is speed of light, divided by lambda. So overall, from here we get that E is equal to hc over lambda, where E is the energy of the photon, right here, energy of the photon in joule, yeah. H is the Planck constant, c is the speed of light, and lambda is the wavelength